Alright, let's take a look at some kind of new stuff for a change. Last week you guys did a lab activity where you created two motions. First you walked away from the detector and stopped, then you walked away from the detector and immediately walked back towards the detector. And we spent some time analyzing both of those graphs. What I want to do today is make sure that you guys understood what was going on there. So this is the last page of that lab, and I just want to make sure that you guys have these answers, right? So number 3, how can you tell from a velocity time graph that an object has changed the direction of its motion? As we talked about earlier, and as you guys saw in those other videos, velocity time graphs indicate instantaneous velocity, which means we get its direction from the sign of its velocity. So if the sign of the velocity changes, its direction changes, and sign changes when it crosses the t-axis. So we can tell direction changes when the line crosses the t-axis. What is the velocity at the instant the change in direction occurs? Well, you got to think about that one for just a second. Okay, say you're moving in one direction and you want to move the other direction. First you slow down, slow down, slow down, slow down, stop. Then you go the other direction, right? So the velocity at the instant something changes direction is 0 because it's not moving forward anymore, but it hasn't started to move backwards. Or if you threw something straight up in the air, it's not going up anymore, but it hasn't started to fall back down. So the instant something changes direction, its speed is 0. How can you tell from a distance time graph, and by distance I mean position, how can you tell from a position time graph that an object is moving at a constant non-zero rate? Non-zero constant rate means that it's either moving closer to or further from the origin, and so that means its position is increasing or decreasing. So it's got to be a sloped line, and since it's a constant rate, it's got to be a straight line as opposed to a curved line. Okay, so on a distance time graph, which is a position time graph, an object is moving at a constant non-zero rate if the line is a straight sloping line. What about on a velocity time graph? Constant non-zero rate. Well, constant rate means the velocity isn't changing, and so that means that the line's going to be horizontal, and non-zero means it just can't be at 0. So it would be a horizontal line above the axis or a horizontal line below the axis. Number 7, how can you calculate from a velocity time graph the displacement of an object in a particular time interval? Okay, that was the whole point of this lab, and this is sort of a big deal. I'm actually going to write it down. Okay, so the velocity time graph shows instantaneous velocity. The slope of a velocity time graph shows how the velocity changes, but the area under it, area under the curve, shows displacement. Okay, remember displacement is change in position, delta x. Alright, so if we can do these two graphs, if we can follow these two directions, then we really should have a pretty good grasp of what's going on with the position time graph and with the velocity time graph. So number 8 says draw a corresponding velocity time graph for the given position time graph and show your work. Okay, so how is there work to show if I'm just sketching a graph? Well, it gets back to how do I get this graph? I want velocity, I'm given position. Okay? How do I get velocity from a position time graph? I have to look at the slope. Okay? So first I'm going to divide this graph up into intervals, and for my first interval I've got t is 0 to 2 seconds. Okay? And I want to find slope, so I got to find rise over run. So my change in position, my rise, delta x, equals 2 minus 0, which is just 2, over my change in time, which is also 2 minus 0. So I got 2 over 2, which equals 1 meter per second. So for the first 2 seconds, I have a constant velocity of 1 meter per second. That looks like a horizontal line at 1 meter per second over here on my velocity time graph. For the last 3 seconds, from 5 seconds to 2 seconds, what's happening? Well, let's go ahead and find our change in position. Our delta x is equal to final minus initial, so 1 minus 2, which equals -1, and our delta t is 5 minus 2, which equals 3. Okay? So, be careful, it's a velocity, direction matters. 1 divided by 3, or negative 1 divided by 3 is negative 1 meter per, negative 1/3 of a meter per second. So up here I'm going to draw this line. It's constant, but it's moving the other direction, so it dropped below the axis. Okay? Make sure you understand what's going on there. We've basically just graphed the slopes because the velocity of a position, or the velocity is the slope of a position time graph. We graph the slopes, velocity is slope of a position time graph. Okay? But now we want to turn around and go the other way. So that's what this says in question number 9. It says, calculate the displacement of an object during the time interval indicated by the shaded region. Well, just think about this for a minute. If I asked you, how far have you gone if you were driving at 60 miles per hour for 2 miles, if you drove 60 miles per hour for 2 hours, how far have you gone? You'd go, well, 60 times 2 is 120 miles per hour. You did rate times time. It's exactly what we're doing here. Okay? Over here we're given a velocity or a speed or a how fast, right? Remember, speed is not a vector. Velocity is, it indicates a direction, but these are all positive, so that's okay for now. Okay, so the trick here is we got to figure out how fast we were going and then multiply it by how long we were going that fast. Well, that's a width times a height. Okay, that's an area. So it says we were going 6 meters per second for 2 seconds. 6 meters per second times 2 seconds equals 12 meters, right? My seconds cancel my seconds. But that's just this first part. Now, why did I have to split that up? Well, because I didn't have a constant speed for this last time. Remember, the slope of a velocity time graph indicates the change in speed. Here, no slope, no change in speed. Here we have this big negative slope. We do have a change in speed. Okay? There's a couple different ways we could go about finding this, but the easiest thing to do is when we're looking for area, that's a triangle, half base times height. So I'm going to take 1/2 times the base, which is from 2 to 3 seconds, so 1 times the height, which is 6, which is equal to 3 meters. And so I'll add those two up. 12 meters plus 3 meters equals 15 meters. So that tells me my change in position, or my displacement, over this whole time interval was 15 meters. Finally, question number 10, which position time graph just from the information in a velocity time graph? Explain. Well, if we come back up and see what we got out of this velocity time graph, we see that we got a displacement. Displacement's not position. Displacement shows us how much an object has changed its position and in what direction, but it doesn't show us where the object actually is. For instance, if I wanted to go backwards from this and I wanted to create the position time graph based on this velocity time graph, I would know that for the first 2 seconds I need a slope of 6, which is a fairly steep slope, right? So I just started right there at the origin, but that's exactly the same slope as if I'd have started up here. So I don't know where the object is, I just know how far it's gone.